So let's get started. So after this class, right, we basically began with this class, then we're starting to take attendance because of actual period is over. So you're too late to drop out of this class, but I think you still can do late drop. No, we'll start counting. So you do the usual, you reply at the middle of the class, and then that will require you to log in your account, and indirectly we know how well you're doing, and then that is how we assess your participation, and of course, depend on how well you are responding on those questions. And just a reminder that since some of you have been asking whether you have want some practice before you have a real assignment comes in, actually you can look at the Blackboard. I have self-checking quiz that's contain many multiple choices. Just I guess as long as you attempt, then you get the full credit. There will be optional tutorial that may cover that, but you once you submit, you have the answer there already. So of course you can attempt as many times as you want, but one attempt is sufficient to get the full credit. So just as long as you do it, then you get the credit for that part of the participation points. So let me continue what we have done last time, and then probably will take us this week. Probably finish all the slides this week. If not, then of course next Monday we are sure by done. Then we'll release the homework one. So just a quick review on probability, right? I think we touched a little bit last time, but we didn't go into great detail. But just to remind you, this is the classical. We start with the classical definition of probability, and that is by talking about random experiment, which potentially we can repeat thing. It's an empirical based explanation. We repeat something and then repeat many times, and the probability is simply a fraction of that. Means by construction is from 0 to 1, right? Is the where the fraction denominator is how many times you run the experiment, and the numerator is the one that how many outcomes that are favorable to the event, right? So this definition by construction must be between 0 and 1, right? Because the maximum you can go for the first one is same as the denominator, so must be 0 to 1. So in that aspect, there's no meaning of negative probability or probability is 200, right? So that by construction must be between 0 to 1. And that is the probability based on something that potentially can repeat all the time. So gambling would be a good thing, right? But you can see this definition doesn't fit very well along application. For example, typhoon prediction, right? We know typhoon is going to be, each time is very different. So how can we run this experiment? We can't really run experiment like this, right? But we know that we can still say some probability, right? That is something that we can still believe, at least in these days, right? The observatory has been very accurate in terms of typhoon prediction. How so, right? So the question is, why we can still say probability, or why does it make sense, right? Do remind yourself, probability is just a statement where you quantify how likely or how certain something may happen, right? And if you recall ourselves why we can say typhoon, right? It's based on scientific knowledge, right? From the data, also from what we learned from physics, which also repeat experiment, we say that the physics law today is going to hold in the future, right? So it is something like universal in the sense that so we can, the knowledge we learn is going to apply, even though that's a different situation. Then if we change the logic, the things still apply. So that means that we have to rely on something rather than experiment, right? We rely on some theory, some knowledge. So we've extended the idea of probability beyond this simple idea of something can be repeated, right? Something non-repeatable still has to assign probability, and then we can derive things from scientific knowledge. Okay? But the thing is how you can make this knowledge-based or data-based probability to be meaningful. Okay, it has start from somewhere, and then we have to start with some what we call axiomatic definition. Okay, if you look at the history, this of the classical definition, or what we call in technical term is called frequency list, is the idea they start from 1700. So like more than 300 years ago, more or less 300 years ago, or 300 years ago. And the thing we learn about modern probability theory, which rely on mathematics, some assumption on that, which we will learn very soon, is only invented in 1930s. Okay, so it's like less than 100 years old, more, about 100 years old, right? So it takes mathematics a long time to figure out what is the structure to get there. Okay, just to remind yourself what are the terminology here. Is random experiment and outcomes, right? And here is we still rely on a wrong die, right? So we know that more or less a fair die means that if you roll 6 million times, right? We say fair if 1 million times roughly is 1, and each number actually is also 1 million times, right? So that means that the probability is just, right? That's the ratio of that, right? Just if you're 1, 2, 3, 4, 5, 6, right? Probably even number will be just 2, 4, and 6, right? There will be 3 million of them out of if you roll 6 million, right? So it's 1/2, okay? So on and so forth. We covered this part, so I'm not going to repeat this in detail. So this is the Venn diagram. If you learn logic, right, this is something that you would have seen. I guess you learned it in your general education class. I'm not going to repeat that part, but this Venn diagram is particularly useful. We use it all the time for this class. But just to remind you, the second thing is about the sample space problem. So roll a die is very simple. We just have outcomes. You record how the die face up is 1, 2, 3, 4, 5, 6, right? But you don't really record where the die lands. First of all, roll a die, right? You don't record the latitude and latitude, right, for that one, right? There are many ways you can measure, right? What's the angle of that, right? But you just measure the number, right? There's something redundant, you don't record it. Same as here, right? You roll the die twice, right? And you record the first result and second result. In that case, the order they appear can be different, right? I mean, you will consider 1 and 2 and 2 and 1 are different. Okay, in sometimes the same, sometimes not. It really depends on the purpose, or depend on how you can measure stuff, right? If the only comes out this total, then you can only record total. Okay, but in this case, you can record the order, then you have 36 outcomes, right? So you really the sample size really depends on the purpose you're doing. Is it the distinguishing different outcomes meaningful? And second is how good is your measurement technology? Can you measure the difference, or you can't? Right? Sometimes just like the data restriction, you can't really measure those, right? Suppose you want to track the stock market, right? And if you're able to track thousands of stock, that's okay, right? But we can't then probably look at the stock index, right? We summarize what happened. Or even the stock market, you can even focus on one stock. How much data you can save is an issue, right? Because the stock movement, starting from the starting trading point, is like, I think it's 9 a.m. in the morning and until 4 p.m. afternoon, right? Every single second, the stock is moving, right? Are you going to record everything, right? And many of time, just record the end of day, the price there, right? So you are not going to record every single details. And the problem is whether single detail is important, or do you have any technology to save those? So that is an issue there. So how deep the sample space is something that have to keep in your mind, but of course it's very, very clear in your exercise, but in your project, in your application, that have to be very careful how you measure those. And let's have an example telling you it's a fair die, right? You want to talk about event, right? In this case, roll it 2 times. Event can be a lot of stuff. Can be say like the sum of the 2 results is less than 3, or less than 4, right? Less than 3, less than 4. Then in that case we have 3 outcomes, because 1 and 1 is 2, 2 and 1 is 3, and 1 and 2 is 3. But if you 2 and 2 or more numbers, then they'll be 4 above. So the 3 outcomes, and these 36 outcomes are equally likely. So that means that if you roll 36 millions of time, we have 3 millions of this outcome. So it's 3 over 36. So it's 1 over 12. So that's how we calculate. I don't see that's a big deal because you have done it in your high school already. But in case you don't know, just a refresh of memory anyway. So here we come to more sophisticated thing because that is how we define modern probability without relying on random experiment. So we simply make some minimal assumption on how probability works, and then we can add our scientific knowledge and data on it. Okay, then we build up our measurement of uncertain world by using probability. Okay, and to do so, we have to define some operation on the event because we have to make a consistent or logical thing because by observation, right, we can observe many things, then the definition of probability is very easy, right? Just outcome. But remember, we want to do it without talking about running experiment, right? So we are learning something from scientific knowledge, right? And the good thing is that the important thing is there's so many ways that outcome or event can come up, right? So we have to figure out that because the data only or the knowledge may only be tell us some part of it, right? We have to construct the other things based on what we call operation on events to complete the whole thing, right? Because to say probability, right, you have to be able to say, you give me any event, I can tell the probability, right? So you have to tell me that how you can combine things and this operation event and how you can combine event and outcomes, okay? And these three are something not new, right? Just like intersection is just and, okay? And union just or, and this complement just not, right? So it's just basically, this is just English and word. This is just oral, and this is not. Just if you learn logic, these are something you learn, and this is how logic extend themselves to the set theory. So if you learn M2 math in Hong Kong, this is something you learn already. But if not, that's okay. Or you learn physics, that is the logic gates that is actually come from there. But don't worry about that. It will be something not so complicated. And those of you who ask why we have to do that, because by doing so, we can create probability without relying on the real world, okay, without experiment. But the cost is we have to give some mathematical complexity there. We just learn some formula there. So the unfortunate fact, but we have to rely on some math, okay? So don't worry, it's something that you know very well. It's not something too crazy. The first one is called intercept. Intercept means an event. So A and B is an event. I combine a new event, okay, combine together by taking all the common elements there, okay? So if a row die, okay, an even number, odd number, okay, and large number, we know already, okay? Even and large, how we do that? You just look at the simplest case and look at all the common element there, okay? And by one of the easiest algorithm is to fix your eye on one particular event and check if this particular outcome is also in other set. So suppose look at this too. Okay, check the even. 2, is it on large? No, then it's not. Is it 4 in E, the second one? Is it also in large? Yes. So this is yes. And check the 6 again. Is it on L? Yes. So that's only left is 2, 4, and 6. That's how you check. So O and L, the same idea. You can check easily. Only 5 appear in both. Okay. So the question for you would be just 10 seconds. Where's E intercept O? Nothing, right? As we said, nothing. So it's empty set. So it's nothing. There's nothing there. So there's nothing common. Well, even and odd, because numbers either even or odd, cannot be both, right? So that means that if you want to write if E and O, usually we write is an empty set. Empty set is like this. Okay. But that was something that we want to be doing. Okay. So intersect by graphic the Venn diagram, if you draw in this way, intersect is the overlapping region for both. Right? So that thing is look at all the outcome that belong to both events. Okay, intersect L. Okay, and if you're okay with this, then we go to the other one. This is something more relaxed one. Union is OR. So A or B or A union B will be you collecting all the outcomes in both. Okay, in either of the is OR, is either of them. Okay, need not be up here both, but anything there, then you pick it up. Okay. So the example again is even, odd, large. Even and large. Okay. Basically, you take everything from the E, okay, to 4 and 6, and look at L. What is not picked is put there. Okay. And by construction, although 4 and 6 appear twice, you don't need to write both because the meaning of the set, this is the curly bracket means it doesn't really, repetition has no meaning. Okay? You repeat the same thing. Okay, because it's just a collection of distinct objects there. Okay, so repeating things is no meaning there. So O and L are the same, right? You can just write them together and take out the duplication, right? So basically just you take everything right together and take out the duplicated part. So what is left is 2 is not there. Okay. So the example for you to think is, what is E union O? E union O is what? Think about that for 1 second. E and O will be just simply S. Right? Because even number or odd number must be the sample space itself, right? Because it's either even or odd. Okay. So that would be the two things there. I don't think it's something complicated, but you may spend some time to familiarize yourself with the U and the union or the intersect, because it looks not so familiar to you when the first time you saw the symbol, but the meanings would be very trivial. Okay, just basically union simply means you would look at a Venn diagram and you try to collect everything there, right? So everything is in the union. Okay, I hope that's clear to you. Okay. Now next is the complement. Complement would be the not, so that is not there. So if you look at the E complement, how we do that? Okay, how do E complement? This means it's not there. Okay, so the example is illustrated. Look at the sample space. Okay, E has 2, so take out 2. E has 4, take out 4. E has 6, take out 6. So what's left there? It will be E complement. Okay, what is not there? And by construction, E complement will be odd, right? Not even, that is odd. And odd complement will be even. So if you look at the odd complement will be even, right? So I guess I use another color to do the large. Large is 4, 5, 6, right? So how you do that? You just take out the 4 and 5 and 6. What's left is 1, 2, 3, right? So that is how you construct the complement. So not something too terrible, right? Something is like something very simple, okay? You ask, okay, why we do something simple? But very soon we will define it and you know what's going on, okay? So just bear with me. There are 3 more terminology we define based on union, intersect, and complement. Then we know how to do it, okay? So that is some operation there. Then we can define probability. Okay. I hope that's not that bad. Well, I'm sorry, there's some notation, but that is something we need to do. So if you write the E is inside, it's even number, then what's outside the E is not there, it's 135. So that's why it's illustrate the complement of E. Okay. Now, here comes several very important idea. Okay. The first is called mutual exclusive. What is mutual exclusive? Mutual exclusive means the 2 events are mutual exclusive if one of them is true, the other must be false. Okay, one is true, the other is false. Okay, do note that you allow both of them are false. Okay, what you don't allow is both of them are true. Example would be, you are in this class right now. It's 3 p.m. I guess. All right. So you're here. So what to give? You can't be having a tea in the canteen, right? So either you're here or you're here. You cannot be in the canteen having a tea, enjoying your tea. If you're enjoying your tea here, you're enjoying tea in the cafe, you can't be here, right? So mutually exclusive. But these two events can be both false, right? Maybe you're lying on your bed on the, in a bed in your room watching YouTube or TikTok, right? So it can be, if that is true, then having tea or sitting here will be false, right? So, but it just forbid that both are true. Okay. So that's why the definition of mutually exclusive is the interset, which is both. There's an outcome that both of them are true, will be an empty set. That doesn't exist an event doesn't exist an outcome such that A and B are true. Okay. So that's usually geographical is a most easiest thing to see, and that's called mutually exclusive. Okay. And the second one is called exhaustive. Exhaustive means that they collectively means that they at least one of them must be true. Okay? At least one of them must be true. So you rule out the idea that both of them are false, right? So mutually exclusive, you rule out both of them are true. Exhaustive, you rule out all of them are false. Okay. For example, exhaustive by English means that you use up, right? So it means that you list out everything in the sample space. In the simple cases, either you're happy or you're not happy. Okay. When I say you're happy and you're not happy, then basically I rule out this thing, right? Either you're happy or you're not happy. Right? So it can't be somewhere in the middle. Okay. Guess there's a standard phrase, at least those who are from Hong Kong would know. When there's a penalty kick in football, there's always a commentary said, okay, now is a penalty kick. There will be two outcomes, either the ball gain the goal or not, right? So that is a very famous statement. I don't know whether you guys are too young to know that, but that is something that we know. But tautology, right, is something like in logic, it's like mutual exclusive, it's like exhaustive. So because it collects. Say it must be true, right? So you have n in general. If you have n different event, right? If the union of all of them together is sample space, that means that it's exhaustive. So now let's combine two things. One is not both of them are true. Not all of them are false. Okay. So combine them means that one thing means there will be one and only one must be true. That's called partition. So it must be the case, at least one of them is true, and at most one of them is true. Okay, that means that only one is true. Okay, repeat I'm saying. Okay. Exhaustive means at least one of them is true, right? And mutually exclusive means at most one of them is true. Okay. So add up must be at only one is true. Let me repeat the statement. Mutually exclusive means at most one is true, right? Because cannot be more than one, right? Because one is true, the other one is not. Exhaustive means at least one of them is true, right? So add up the two things must be at least one, and the only one is true. Okay. So that is what we see. So we say everything is partition, which is exhaustive and mutually exclusive, means one of them is true and only one of them is true. So it's hard to remember. One is easy to see this graph. That's what we do in the birthday, if you eat birthday cake at all. So what we're going to do, imagine there's a cake in the sample space. Okay. A partition simply means we cut it into multiple pieces. Okay. I'm thinking cut the cake is non-overlapping. So it means that we only will take one of the cake, pieces, right? And only one will be taken for you, okay? Unless you are very selfish, you take more than one, but suppose you are not that selfish, and want to take one pieces, right? And that is what happened. That is called partition, okay? Is that clear? So that is very important. We will see very soon why we need that part, okay? But bear in mind, mutually exclusive is the most important concept, which will be defining our model, okay? So remind yourself, mutually exclusive is the most important thing. Now, once we have that, then let us define. Sorry. Let you give example on the example. Sorry, give example on what is exhaustive, partition, exclusive. So we have again, row is die, 6-phase die, even, odd. P is the prime number. B a big even number. Okay. And first, you will see O and B are mutually exclusive. Why? Because if one is true, the other cannot be true. Okay. If odd number is there, okay, it can't be big even number. Okay. Of course, you can see O and E are also mutually exclusive as well, right? Because there's no common element there. Okay, remember. Collective exhaustive means the union of them must be sample space. Okay, you write down all of them is sample space. So you can see OPB is collective exhaustive, but of course, E and O are also collective exhaustive as well. Okay, even odd number, so be exhaustive, because collective exhaustive means that look at every element in the sample space, you can find any of them, right? You can find one of them from there. And let me repeat this. Okay. Why is collective exhaustive? Why is collective exhaustive? Look at this, okay? Why is collective exhaustive? So one can be found from where? Is OPB, right? So one can be found from here. Look at two. Two can find from here. Three can be here and here. 4 is here. 5 is here and here. 6 is last one, right? So as long as you can OPB together, you can find something from the S, right? Everything S can be found in one of them. It can be more than one, but at least one of them, then is what we call collective exhaustive. Okay. And you can see E and O are exclusive and exhaustive in the sense that if E is true, O is not true. O is true is not true. Okay, but together they become a sample space. Okay, is that clear? So the definition is not complicated, but just have to get back to the definition to know it. And as I said, you don't have to memorize, just understand them, then it's fine. So I think that's what we said, right? Is most one of them, at least one of them goes through. That is why one of them, 1 and 1 is only to happen. Okay. Now, after that, now we're ready to define our probability. Okay, which we will not use any random experiment. Okay, it's just some numbers. And the modern definition of probability is just a function. Okay, it's not a number, but it's a function. Okay. What is function? From math class, you learn function is you give me something, I give you something, right? And this probability is that you give me the event, I give you a number. Okay, because this is what probability does, right? It's a number from 0 to 1. Okay, that's what the first assumption said. The first assumption or first axiom. Axiom is something we don't check. We take it as given. Okay, this is something we accept to a probability. The first thing we accept is the probability you give a number. Okay, I'll give you a number. The probability must give you something from 0 to 1. Okay, you may ask, okay, isn't it trivial? Not there yet. Later we talk about odd ratio, which is something from 0 to infinity, right? Need not be 0 to 1. Okay, to measure something uncertain, need not be 0 to 1. In fact, in the old days, actually 0 to infinity is, later you will see, is something that historical people use it. And probability is something that we invent later. Okay, but do know that the first thing is you give me something from 0 to 1. Okay, the function. Okay, this is nothing new there, but this is something we need to make assumption on what kind of function, right? It's like you give me an event, I give you a number. The second one would be saying that if you give me the sample space, the whole thing you give me, I'll give you the maximum number one. So this is something required to say it, because that means that I know everything there, right? There's no surprise. As I told you in the first class of this chapter, right? If I put my hand into a head, right? I should expect maybe hair, maybe something else, right? But there's never exists a rabbit comes out, right? So that would be something, it's not magic. So something you would expect, you know that you're surprised this comes out, but not why actually this comes out, right? Because you're only surprised by this unlikely thing comes out, but not actually why this outcome comes out, right? Because you never expect to happen, right? So that is the idea. Now here you may say the first two are really trivial. Yes, this is really trivial. The bite comes from the last one. This is our last axiom. This last axiom actually basically is giving us the idea of probability. Without that, there's no probability. So this is the key thing about probability here. So you may ask, okay, what is this most important axiom? It's the following. So if an event that have outcome that is mutually exclusive, okay? So basically the event have different outcome, cut them in different parts. What is said, the probability of that event will be same as the probability of each outcome add up together. Okay? So it's what we call additivity. Okay? So you can say there's a very complicated event. Okay? I divide it into multiple mutual exclusive events. Right? So they can't happen at the same time. Mutual exclusive, one is true, the other is not. So the probability of each this outcome add together must be same as you calculate as a whole. Okay, the probability of the whole is probability sum of its parts. Okay, as the parts are not overlapping, right? So no duplication, right? So it must be true. So that is what it said. This probability A is probably the union of all the outcomes, and these outcomes are mutually exclusive. It means that it must be equal to sum of all the probability of each outcomes. Okay, so there's a very important idea behind. Okay, you can imagine this is nothing new, but you learn from the primary school, right? Or even kindergarten, right? Suppose I want to measure how long is this, whatever thing you may call, right? You can measure it all at once, but measure it part by part, right? The same thing, right? So that's exactly what it is, right? Or you want to measure the height of this building, right? So you can able to find a measuring tape from the ground floor to the top floor, once and for all. But or you can measure the height of each floor, adding each floor up, right? It should be the case that the height of each floor add up together must be equal to the height of the building. Okay, if not, then we have something else. So probability only have to restrict on this one. Okay, otherwise it can't become something else. Okay, the probability have to restrict on this one. Okay, and probably ask, isn't it trivial? Yes, almost trivial. Okay, and this one is usually not a problem when n is a finite number. Okay, and that turned out that why mathematicians take them for 200 years to figure this out is n for infinite. Okay, and you ask why we care about infinite. Okay, in the next chapter you will learn that when things are finite, infinite are very different. When they're finite, we can use something, we can list things out. When infinite, then not easy. And for example, what's infinite? For example, what is the you have infinite possible outcome? Like say when you talk about the probability how many customers would come is 0, 1 up to 10, right? Or even infinity is fine. But when you talk about, say, what is the temperature, right? Temperature is infinite, right? Because any number would work, right? Depending on how good a measurement you are. So when you go to infinity, then you require actually n to the infinity. So there is something a little bit tricky about that part. But just go back to the normal case. Suppose why this makes sense, right? Because you want probably even numbers should be equal to the probability of 2, 4, and 6, right? If not the case, then it really about the probability can be troublesome, because It really depends on how you look at the stuff, right? So this is something that we have to make sure probability works. This is very single most important thing. Okay, and let me give an example why these axioms allow us to assign probability without running random experiment or without relying on random experiment. This example. So we call this example, we know very well, it's 1 up to 6, right? Okay. So how do we define probability without running experiment? First, by axiom 2, axiom 2 said what? Means you give a sample space, I give you 1. So the first bullet point said probability of sample space is 1. So fair enough. So now we use the second bullet point, use axiom 3. Axiom 3 said what? If you give me an event, I look at each outcome, as long as they're mutually exclusive, I can add them up. I can calculate one by one, right? So if I give you the S, there were 6 outcomes, of course, they are mutually exclusive by construction because you have 1, you can have 2, you have 2, you can have 3, right? They're mutually exclusive. So probability sample space will be adding up of each outcome, 6 outcomes. Is that clear? Now come with the third bullet point. So, sorry, the fourth bullet point, okay? The fourth bullet point is, now the key comes in, is about our scientific knowledge and about our data or assumption, okay? And suppose, just for example, now we impose the assumption that the die is a fair die, okay? It's done engineer perfect. You do not need to, but suppose it's an engineer perfect. That means that each outcome should be equally likely, okay? By experiment or by construction, right? By science, right? Suppose we don't test it, right? We can't run experiment. But suppose we design the engineering, the dies is so nice, everything looks perfect, it's symmetric, okay? Then we expect, right, each outcome is equally likely, right? Then once you solve it, that means that PR, they are all equal together, okay? Y to the 1/6, you solve the equation, right? How we get that? Just to remind you that we have, they're all the same, right, miss? So that means that they're equal to X, which are known, right? And this from the, is 1 from here, right? And they're all X, right? There will be X, 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 6X, right? 6X equal to 1, which means what? X is 1/6, okay? Then we can calculate everything there by axiom 3. Even number is adding up of 2, 4, and 6. That is 3/6, right? But do know that here we just use we don't run experiment. What we run is our knowledge about the die is perfect, symmetric, we get that. But this need not be the only outcome, right? But maybe you are cheating the die, you put some asymmetry of the die, maybe one is more likely than the other, maybe twice more likely. Say, for example, suppose it's the case, then you have 2X here, right? Say X is more likely, right? Then X will be 1/7, right? So that means that one will be 2/7 and the other 1/7, right? So that is based on engineering. We can decide that. We don't need to do it without, we can do it without experiment, right? So here is what data comes in. Here, what is the scientific knowledge comes in, because we can't repeat things, right? But how can we assign probability? Based on our knowledge. And then we make some assumption there, we can assign those things. So there's no need to repeat things, okay? As long as our data, our scientific knowledge, okay, saying that this is appropriate assumption, which of course depends on how good your data or knowledge is. Of course, garbage in, garbage out, right? If you make the wrong assumption, you get the wrong result. But assume you get a good knowledge and you have a nice thing, you have nice data, then you can predict the future, right? You can say about the future very nicely, you can quantify the future, right? Let's say the stock market, right? You use the good data, if the future is something similar in the past, right? So that gives you a good prediction of what's going on, right? So that is how, so far, we have been using without using repeatable experiment, right? Something non-repeatable can be replaced by our knowledge, replaced by our data, okay? If you think that our knowledge and data is still applicable in the future to your thing you want to predict, that is a good one, then what you have is there, We don't need to repeat things. Okay, so there's a huge jump from what you learn in high school to the college level, because so far we can teach you how you can use your knowledge to do probability, right? But of course, in our class, we're not science class. We are not doing other data thing, but these things can become data, right? The data can tell you how you estimate those, right? Data tells you what are the thing, what need to adjust, and once you put it there, you can predict probability, right? Then you remember what's used probability is to quantify uncertainty, right? Use knowledge on data to generate those prediction. And that's not our class would do. You have to study more advanced class, right? If you use marketing, you learn marketing theory, marketing data, how to assign this probability. You learn the finance, then you learn how to use financial data to assign this probability. It's not my job to tell you how to do it. It requires you to study those knowledge there to apply. But we tell you the tools, now you can impose those. Okay? Is there any question? So you pretty much, we summarize the improvement of probability theory from 1700 to 1900, right? You take mathematics 200 years to come up with this. Okay, you learn it in 45 minutes. Okay, is there any question before we have a break? Okay, if no, then let's have a 15 minutes break. After that, we talk about different probability rule. And just to remind you that we're doing you reply in the middle of the break. This part can the participation attendance. So please make sure you fill in. So break. Let's resume at 15 minutes after. guess it's a good time to check how well you're doing. So please try to fill in. If not, because I will end the thing once I finish discussion, I will end the status. Have doc today? No. Blue Monday. What's DOTE DOTE? Is it something I don't know, but good anyway? Everything is good? Yep. Oh, so one of us think is today's Friday, so not there yet. We still have 4 days to go before we enjoy our holiday, but we just have done our holiday. Yeah, I think there's some rain there, but somewhat of most of our things sunny. That's good. Yep. One of the key point, but I guess the main thing is we learn the modern definition of probability, which we do not need to talk about random experiment. Can be come from data, can be come from knowledge, from scientific knowledge. This is the very important. See, you can, some of you have seen that. I mean, the axiom is very simple, right? So it's a function that gives you a number. But of course, the number is actually a percentage, right? Because it's from 0 to 1. And yeah, U means or. Technically, right? But English means or, but it's taking all the element that in either of these events. So almost everything is okay, not too fast. I'm glad that most of you can follow. I mean, mean is pretty high, so I'm very happy. Woke up from a nightmare that the class started an hour, but yeah, it happens. Let's watch this later, but let's see if anything. Tired. Yep. I think everyone's probably I think it's kind of interesting, although the math itself is a little more complicated, but I guess it's because probably it's just like the way that we look at in the future, in an uncertain world that many things can happen, is a way to the language to describe from our scientific knowledge and data, which outcome are more likely than the others, right? So that is the main thing. There's some video, I don't know what it is, but hopefully it's not the scam or the something that, oh yeah, it's a good one because every year they have some trap for me. Yeah, but I'm not going to play them, but you can dig it out because I've listened to this many times already. So have fun. So now let me continue our journey. Okay, just to remind you a little bit. Again, what we have done is the 3 axioms. That's very important. The first axiom said, you give me an event, I must give you a number between 0 to 1. Okay, it's not about fraction, but just 0 to 1. So that's no fraction thing. And if you give me the whole thing, it's equal to 1. And the third one is if many outcomes together, okay, and they're mutually exclusive, okay, you can count the whole or you count part by part, okay, as long as they are not related, okay. So that is the idea there. Now, once you have that, then we can talk a little bit more what you learn in your high school. Some of you have learned that, but we're just saying that all the rule actually can derive from the 3 axiom we impose. The 3 axiom tell us everything that we need for the rest of the class. Okay. The first rule we want to learn is called the complement rule. Complement rule simply means the following. It means complement is not, right? Complement rule means I carry the probability is equal to 1 minus its complement. Okay. And why it's true? Because that's actually come from the axiom 1 and axiom. So it come from axiom 3 and axiom 2, right? Axiom 3 would say the sample space, which is the probability is equal to 1, right? And sample space can be decomposed in A and A complement, right? So the adder must be 1, right? That's proved in the next page, but I'm not going to prove it. But basically said the sample space is 1, right? You cut the sample space into A and A complement, right? The whole thing is 1. So 1 minus itself, 1 minus that part, we go to the part you want, right? Instead of going to this, we give an example why this is true, all right? So this example is not something terribly difficult. Full screen there, okay? So you want to look at the die that was the face value less than 6, okay? So to calculate 6, you have to look at, okay, roll a die, you have to 1, 2, 3, 4, 5, right? And of course, if you're able to know what's probably 1, 2, 3, 4, 5, then you're done, right? Because you know that that is less than 6 1 to 5 means it's 5 over 6, right? If there's a fair die, right? There's 5 outcome, it's equal likely there's 5 or 6, right? But sometimes you don't really know how to do 1 to 3 or 5, right? Because in the knowledge, you just know the probability of 6 will comes out. You don't know 1 to 3 or 5, right? Because to know the 5, you need to know the data and knowledge of 1, 2, 3, 4, 5, how they comes about, right? But you only know 6, right? And this tells you that you can still do that, right? Because probability of 6 is 1 of 6 in terms of fair. If not fair, it can be any other number, right? But at least, even though the die is unfair, or maybe any imperfection, as long as you know the probability that you get 6, right? You can calculate less than 6 by 1 minus. Regardless of the die is crazy die or some unfair die, tricky die, doesn't really matter. You don't care about how 1 up to 5 looks like. You know the 6, 1 minus the 6, you're done. So that's very important because you see a lot of time when you calculate probability, that is very important because we don't know how 1 to 5 looks like, but we know 6. So that is one example we want to say. Okay. So that is, I don't know how many is there, how to estimate those, but I know what's outside. By subtracting from 1, then you're done. Okay. I'm skipping the technical because I guess if you want to know, you can easily read that. It's not something complicated. I focus our time on something more important. And the second implication we want to talk about is what we call the addition rule. Addition. We know that from axiom 3, okay, if 2 outcomes are mutually exclusive, okay, you can add them up with the same as the probability of their union, right? Because axiom 3 said, right, the whole is sum of its parts, right? You can calculate both parts and add together, then you're done, okay? But do note that the idea axiom 3 is they're mutually exclusive, right? So if whole is sum of its part, whenever you don't have overlapping, right, which is intuitive, right? But what happens if they overlap? How can you do that? Right? How can you do that when they overlap? So the idea is not complicated, but you just take away the overlapping part. Why this whole? Of course, we rely on the math, but I can convince you that there's something you learn in the kindergarten or primary school. Let me look at this picture. Okay. A and A union B, of course, they are not mutually exclusive. They have common element, which is the pink area. All right. So if I want to have the union, which is this shape of A, right? And then what I have to do is you can look at the red circle, you plus the purple circle, right? But in that case, you double count the pink one. So that means that you have to red area plus the pink circle, sorry, plus the purple circle minus the pink duplicated region, get back what we want. Okay, you get one to that this glasses area. How can you do that? You get the red circle, purple circle, take with double counted, overlapping, duplicated region, pink, you're done, right? That's why it's probability A plus probability B minus the probability A intersect B is equal to probably A union B. That is what it says. Okay. Of course, you can swap the unit intercept. You give you other rule, but this is the rule that easier to understand. Okay. So you can know the intercept and the complement can calculate easily by swapping things out. Okay. So that is very important rule. Okay, probably you still abstract to you. So let's give example to see why it can be useful. So if we often roll a die, so let's continue the die example because it's easy to understand, everyone knows it. So roll a die. Now if you have the first event called A, which is even number, which is 4, 2, 4, and 6. And there is an event B, actually it's a large, right? It's 4, 5, 6, right? I use A and B, but you can use E and L that we have been doing. And A and B is even number greater than 3, right? So if you look at the intercept, you just look at the common element, you only have 4 and 6, right? Because only 4 and 6 exist in both. Okay. So now let us illustrate this. Is what we ask is how likely is even number, or so what we ask is this guy. Okay. Or no, this guy. Okay. Let's calculate this directly first. Okay. And then we understand why the formula works. If you look at this, A union B is going to be 2, 4, 5, 6, right? You know it, just pick up every element there, right? Because even is 2, 4, and 6. Large B is like 4, 5, 6. There's 2, 4, 5, and 6. So if this die is fair, you have 4 outcome of 6 outcomes, so it's 4 over 6, 2 4. Okay, so it's fair, easy, right? But sometimes this is very complicated. Okay, so what we're going to do is look at this table, right? So sorry, look at this data. Probability of A, which is even, is 1/2 or 3 over 6, right? And B is greater than 3 is also 3 out of 6. And A intercept B only 2 outcome is 2 over 6. So just add up minus this, right? Is the red plus the purple minus the pink. So red plus purple minus pink, which is 2/3 as well. Okay. So you ask why we have to do that? Because very often this is how you get the data. Okay. In your from the business data, right? Suppose you want to ask maybe this insurance company data, right? A, maybe someone gets some disease, A, right? Some particular disease A, and B is probably the people who got this B, right? And A and B is like the guy who get A and B together, right? So then you want to know what's OR, right? Because then you can do this calculation where often you do this. Okay, so you can go back and forth to ask this kind of question. So let me give you another example that often appear in our data, like this question. I mean, I promised to talk about two-way condensate table. Now I come back to it because remember this table in the first class. So this what happened. Not our class, but just some make-up number. But we have 80 students in the class, and look at who passed exam and how they define by data. Okay, with the gender. So you can see the first upper left corner of the table, right, is 15, which is 15 male passed the exam, and the second number is 25, male failed the exam, and you have 20 female either pass or fail, right? And the columns and the rightest column and the bottoms is the marginal, right? It's like 40 male, 40 female, 35 pass and 45 fail, and total 80. Okay, this is how the table is being read. So the question is, what I want to know is how likely that a student I randomly pick from the class is either male or pass exam, right? Why we want to do that? Maybe I was asked to send a student who is a male to participate in the male competition, right? Okay, that is something I want to do, right? Or something like that, right? So in that case, how are you going to do that, right? Let's do it directly. like this one, like directly do this one. So who is the male or past exam will be, this is the male, right? Past exam is this one. So that's why it's 15 plus 25 plus 20, all right? Over 60. So that is, you get directly answer. Okay. But you can also do it the other way around. Okay. Of course, we say this is stupid. Why this so long? But if you look at the table, if the table is very huge, then this method will make more sense. Okay. Let me illustrate what is the method here. So what I going to do is look at why this is easier. What I do is I look at what is the male, which is this number there, right? With male or past exam, I look at how many male there, look at this number. I look at how many people look at past exam, is this guy. Male and past is this guy, right? So I add this and subtract from this one. Okay. Then this is how I do it, right? This and calculate this and subtract it, I get the number. So imagine this table is very long, very complicated. You add up many number there, but instead you look at the very end and the free number, and I'm done. Okay. So this is much more convenient, other than you have to pick up many numbers down to add up together. So this is why this is way more convenient. If you imagine there are many categories in one dimension and the other one, then this definitely much faster. Okay. But of course, this illustration, of course, later you will see calculation. If it ever happen, this is much easier. Okay. Is that okay? Because remember, if you have to do the direct way, you have to add up all the number in the both row and column. But if I do the way that indirectly, I add up these two n number and somewhere in the middle, then I'm done. Okay, just free number there. I don't need to add up many columns, many rows. Okay. So this is the last formula we gave you before we go to more advanced. This is what we call the total probability rule. Okay. The total probability rule is very similar to axiom 3. Okay, based on axiom 3. And axiom 3 said what? You have a event, right? You can cut it into many different pieces. As long as pieces don't overlap, adding up all the pieces is same as look at the whole, right? So the same here. I look at A, okay? It can be A with B and A without B. Okay? So A is going to be A with B and A without B. Is that okay? So this is the definition, right? The A, the red circle. A with B is the pink one. Okay? A without B is like the smiley face. Right? That guy, right? So let me specify again. This is A with B. This part is A without B. Okay? So A is A with B and A without B. So that is very simple. Now it's not more general. If B is the sample space, so B is the partition sample space, B1 over B, just like S, you cut into many parts. Okay? It's B1, B2, B3, B4, B3, right? Just the sample space cut into many parts. For A will be A with B1, A with B2, A with B3, A with B4, A with Bn. That's it. Okay? So that would be the idea. Okay? So that would be the calculation. Now, once we're done, then I want to talk about this part, because this is explanation why we want to talk about modern probability. It's a connect to the way old idea, odd ratio. I mean, odd ratio is way beyond back to the long time in the history in the old days. Okay. So let me define odd ratio. Okay. And odd ratio by construction is this. Look at there are two ways to define, but usually we use the above one, but you can see this swapping the denominator. But this usually we don't say in favor or against, usually mean the first one. So usually we use the first one. Okay? It's the probability A over its complement. Okay, and by construction, you can see that if probably A is 1/2, A complement is also 1/2, right? This is 1. So odd ratio is 1 if something is equally likely, right? Whether A happen or not happen is going to be 1, right? So usually we say 1 is something like, it's very easy to see, right? Something is whether happen or not is equally likely, that's 1, right? So that is that, right? And actually this is something that odd ratio itself is there's a 1-to-1 relationship between odd ratio and probability. You give me probability, I can give you odd ratio. You give me odd ratio, I'll give probability. Okay, what do I mean by that is this. Is this graph. If you give me probability, I can give you odd ratio. And odd ratio is, if you look at history, is probably the oldest way to describe probability. So odd ratio to infinity means it's close to 1. Odd ratio of 1 is 1/2, and so on and so forth. Okay, you may ask, whatever, why do we use that after that all? Okay, very soon. Okay, this is very closely related to betting, casino, very soon. Okay, but bear with me, you will see this is happening in the casino here. So let me define it. Okay, so this betting odds in casino that's actually is actually related to the odd ratio, and indeed that's why we say odd ratio is more older than probability, because gambling, right, start way before mathematicians about probability. Okay, of course, probability, you learn the history, is because the mathematician want to do gambling, right? They want to figure out what is the way to fair bet, but gambling start way before people think about gambling. Okay, so you look at the betting industry, they give all the time they give you the odds. So usually they call odds of 4-to-1. Okay, suppose in particular, suppose odds of 2 soccer team A wins is 4-to-1, means that if you bet $1, if the team A wins, they give you $4. If you lose $1. That's 4-to-1. Okay. So the question is, okay, if this bet, okay, is a fair bet, okay, which means that the casino is not cheating, they're not earning you, they give you this is a right thing, or we think that fair is like if you bet this long enough, okay, there's no winning or losing, because you can bet team A win or team B wins, right? So or they draw, right? You can bet anything. So as long as the betting is competitive, then the fair bet is actually related to the odd. What do I mean by that? Okay, let me give an example. Okay, if you roll a die, okay, what is odd of getting, say, particular number 6, say, for example? Okay, if a fair dies, then the probability of 6 is 1/6. Okay, odd ratio will be 1/6 over its complement 1 minus 1/6. So it's 1-to-5, right? So it's 1-to-5. So I would say, okay, the odd ratio is simply 5-1. What does that mean? Why this is a fair bet means that if you're a casino, you run this in a long time, you don't win or lose. Okay, because if you have, suppose you run 6 million times, okay, you will win 1/6 of time, right? 6 million times. 1 million time is 1. 1 million time is 6. 1 million times 1, 1 million times 2, right? So you won 1/6 of time, right? As you, and then 5 or 6 times you lose. So you lose, when you lose $1, right? So if you win, how much dollar you have to compensate? So 1 time you lose, 5 times you lose. So if you win $5, right? Because 5 minutes time you lose. Every time you lose $1, right? 6 million times, 5 times you lose. 1 time you win, right? You 1 million times. So how much you have to earn? $5. Okay, so the casino is fair, right? Which, because you can buy both sides, right? You can buy whether 6 comes out or not, right? So in that case, which is fair, so the odds will be 5-to-1. Okay, Is that clear what I'm saying? Let me repeat because I think this is a little bit tricky. Okay, let me repeat. So if I roll a die, the die comes out number 6 is 1/6 if the die is fair. What's odd ratio? Odd ratio is itself minus over is 1 is complement, which 1 minus 1/6. So you calculate that is, let me write that down because that would be more clear. So the numerator is 1/6. The denominator will be 1 minus 1/6, right? So that means 1/6 over 5/6. So that's just 1/5. Okay. Then in that case, if the casino is fair, or which will be the case because many competitor, because you can buy both sides, and then usually this is a fair or more or less fair. Okay, not exactly fair, but more or less fair. Then you will get the odds is 5-1. Means you win, you should win $5. Lose $1. Why is the case? Because you supposed to pay this game 6 million times. Okay, 1 million times is 6, and 5 million times is 1 up to 5. Right? So if you won, you should win $5 because 5/6 times you're losing. So because you lose $1 for 5 million times, you have to win $5 for 1 million times to cancel that out. So you're not winning or losing. There's a fair bet. And I would say there's an economics or finance. Fair bet means you're making 0 profit. Okay, and you learn economics from your other class, right? Because many casinos, then no one can make any profit, right? There's 0 profit condition, free entry. Okay, not going to talk about economics. Although I'm an economist, but forget about that part. Okay. But you ask why we care about this. Okay. The reason is because of in a lot of cases in the world, we don't know probability, but we know the odds. We know the odds in the casino. There are many things you can bet. The poly market there, you can bet, right? Look at the football game, right? In Hong Kong, you can bet, right? Team A versus Team B, who's going to win? Then you know the odds, you know the probability. Same now, I think now government is thinking about allow basketball to be bet, right? And looking at the betting, you can know the people's probability because people buy Team A win, Team B win, right? Because they put the real money in, and actually the market will tell you what is the best guess of which team will win, right? And of course, someone will say, okay, I don't care about betting or sport. Okay, put that down, but look at financial market, right? Financial market, you can look at people, look at the futures, right? Look at index. Then they look at up and down, they can look at the price, you can, same idea, you can estimate probability, right? It's similar to actually those of you who learn investment class, right? One of the famous thing about the pricing, the option pricing, right? Black-Scholes model, right? And people actually use the Black-Scholes model to back out what they call the implied volatility, right? So you can use the market to infer something exists in people's heads. Okay, so this is very good, right? Probability, sometimes you cannot really get it, right? But we can, from the betting market, we can get back what's probability, right? So for example, in Chicago, right, there's a lot of betting on the weather, right? By looking at the betting, we know we can back out what is the future temperature, future weather forecast, right? Of course, you may say it's good or bad, but at least this is what people think, right? You may not say maybe all people are wrong, but that's okay, right? But at least you know what's going on when people think. Okay, so that is the idea. Is that okay? So that's why it's very good application there. Looking at the odds, we can go back to probability, right? Same as the horse racing, right? Suppose you now learn this class, right? Even though you don't know any horse, you go to starting, okay? Someone asks you which horse is going to win, okay? Probably you can figure out that which odd is lowest, that is going to win, and they can also say which one is more likely than the other. By how much? Look at odds comparison. You can calculate those. More difficult, right? Now you can know how people would think which horse will come out by how much probability there. You can guess. You can accurately estimate those. Okay. That being said, disclaimer: I'm not saying that you should do betting because I never do betting anyway. So just saying that you can estimate that, right? So not asking you to go to casino, go to do horse racing betting. Okay, just for calculation purpose. Now, again, so far, the probability calculation is very simple, okay? But now we want to talk about something very important. which I don't think we can finish, but we'll continue next class, is about updating. Okay, and we start with conditional probability. Okay, before we do that, why we want to talk about this conditional probability is, if we learn something new, okay, how can we update ourselves? Okay, and that's what happened every day when we learn about typhoon signal, right? We have 3, we have 8, we have 9, we have 10, is of the observatory, looking at the new data, looking at where this typhoon is, update how close they are, right? Sometimes the typhoon signal can go to 1 to 3, but 3 to 1, and go to 3 again, go to 8, and come back going up and down, right? So it's like new information, how we can update our knowledge, because probability is the statement of what may comes out, right? And how likely one thing will come out, right? But if you learn new information, how are we going to update it? All right, and that is later we learn the most important in this class, the Bayes rule. Okay, Bayes rule is the way that how is update. Okay, it's what we call probably you say the rational learning of humans how people should learn. Okay, of course, that actually you would imagine that's what we call these days machine learning, right? And Bayes rule, Bayes theorem will tell you that why the machine how should learn is that Bayes learning. Of course, if you go to engineering background, you will say Bayes learning is not the only way. Okay, there's some other way that can be faster, but Bayes learning still the main criteria that how machines should learn. Of course, this is a basic starting point of how we learn things in probability sense. But before we do that, we will define one thing we call conditional probability. Based on that, we can start to learn how to say how we should learn. Okay, but it's not complicated. If you ever learn this, it will be complicated because this is I think it's in the if you learn local execution system, you learn M1 math, you'll be there. Okay, but if you do M2, then you never learn that. So what is this conditional probability? Is we have something very crazy notation with A, but you have a vertical line B. What does that mean? If we know B had happened, okay, now then what's value A? Of course, A and B are not the same. If A and B are the same, then you're done. It must be 1, right? If A and B are the same thing, right? That must be 1. But A and B are the same. If I know B happened, how we update the thing? Okay. So that is the idea. Look at A. What we do later will make sense is a fraction. Is A intercept B over B. Okay, so that would be the idea. Okay, so you may ask why this makes sense. Okay, let me give an example, and then you see why this would make sense. Okay, this is, of course, you can prove it, but I'm not going to do the math. But the main idea is, you know, B had happened. Okay, so the sample space strength. Okay, not knowing S, but the B. So, but remember, axiom 1 set must be, the probability must be 0 to 1. And some axiom 2 said the sample space must be 1. So to divide them to make sure that it's still between 0 to 1. Okay, because when A is B, this is just 1. Okay, because A intercept, if A is B, this is just B, okay? And B over B is 1. So let me give an example. So let's look at this example. Is I have a die is 1 to 6. Again, E is even, and large is 4 by 6. And E intercept L is 4 and 6. Intercept means you take the common element there. So the question would be, I'm asking is, I know the die outcome is large, which I know is 4, 5, and 6. How likely that's even, which is 2, 4, and 6? Okay, that's the question. I know it's large. How likely is even? Okay. Now, of course, you can do what you do is you can rewrite the question is the sample space is no longer 1, 2, 3, 4, 5, 6. You know the sample space is now is only large, which is 4, 5, and 6. Okay, and even it's just 2, 4, and 6 because 2 is no longer relevant, right? So it's 2 outcome or 3 outcome is 2 over 3. 2/3. Okay, so they're done. Okay, but that's direct application is using formula there. Probably large is 3/6. E and L is 2/6, and it's 2/3. Okay, so that is the idea. Is that clear? So that's the case. Okay, so is that clear? What's going on? And so the idea is like this. The graph is before it's 1, 2, 3, 4, 5, 6, but now I tell that large had happened, which the sample size shrinks to the smaller one. You are asking how likely that even as occur, right? So basically, just look at the purple region over the red circle. But of course, you can do it from scratch. Okay, this is what we have done. You can just do it directly. Okay. And this is how you can apply using this simple example there. If you have even A is 0.2, B is 0.5, A and B is 0.3, then what is A given B? Just apply the formula there. Okay, give you 1 minute to look at it. Okay, I guess that's fine. Is that okay? So probably you ask, okay, why we need that? Why we need that? Okay, why we have to do that? I will give you many examples, but one example is condition. No, probability will be very important, very useful when we do multiple things sequentially. Okay, with this example, and that or the time dimension is important. Okay? Then it will be very important, very easy to calculate probability. But before we do that, I introduce a rule that is called multiplication rule, which is nothing but look at this formula again. You multiply both sides by probability B. Okay, you multiply both sides by probability. Let me write that down. You multiply by probability B. Probability B here. Multiple both sides, right? As long as it's not 0, this thing cancel out, right? And what you left is B, probably B times A given B is probably A and B. So intercept can be written down into this way. That is called the multiplication rule. Okay. This is a rule we have. And you see example that this rule is very convenient. When you calculate things happen one by one, and it's very common in finance or common in the world, right? Because you think things evolve one thing after the other. So A and B is B given A times B or A given B times A. Okay, because A and B has no meaning, can swap A and B, right? A is B, B is A, then it's the same thing. Okay, but now let's give you the example here, show you why this is very useful. So this is very common example in probability books, textbook. You see people draw balls from urn. Okay, from a boat you can draw twice. Okay, this is very useful because you draw without putting back the ball. You draw something there, then put it back. So the first draw is different from second draw because it depends on what you have drawn. Things are different. So here we have 3 black and 3 white balls. Okay, and now suppose I close my eye and draw first ball. Okay, and draw again. So how likely that I draw 2 balls are black? Okay, of course you can easily write this. I have 30 outcomes. Okay, because the first time I can draw 6 balls there, and second times I have 5 balls to left. So later you can check, and I think in first day you would know actually we have 30 different possible outcomes, right? Because the first time you have 6 possible balls you can draw, the second time you have 5 different balls you can draw. Okay, you can calculate this particular, you can count how many there are there, right? Because why I say that? Because you have, so you can draw a table, two-way table, first ball and second ball, right? You have, suppose you name the ball 1 up to 6, right? And ball 1 up to 6 there, right? Because once you have drawn, you can draw again, so the diagonal or not possible, okay? And how many, each outcome is equally likely, and then how many entry you can have is 36 minus 6 is 30, right? So there's 30 outcome there. And you can count how many of them are black, right? Because suppose 1, 2, 3 are black, 4, 5, 6 are white, you can just count, okay? But this is very tedious. I don't want to do that. So I tell you that you can calculate that very quickly, okay? Without doing this kind of crazy calculation. So let's do this. Let's define the event. B1 is the first ball is black. B2 is second ball is black, okay? So probability B1 is very easy to calculate, which basically is you have 3 balls, so 6 balls, out of which 3 of them are black. So you close your eye, you draw one of them is black, is 3 over 6, which is 1/2. Okay. The second question is, can we calculate probability B2? Yeah, not that easy because it depends on what happened in the first round and so on. You can do that, but let's not worry about that part. Let's calculate this. B2 given B1. Suppose you draw the first ball is black. Okay. What does that mean? Now you have 5 balls left. You draw 1 black, you only 2 black and 3 white. So you can draw the black is 2 over 5. That's it. Okay. Why useful? Because the multiplication rule said B1 and B2 is B1 times B2 given B1. So B1 given B2, right? So just multiply them together and you're done. Is that clear? So nothing new there, right? Just multiply, right? Just 1/2 times 2/5 is 1/5. That's it. So very simple, right? Just like you don't have to count for the outcome and how many of them are black, right? You don't have to do that. So life is easier in this thing. And very soon you will see why we have to do that, because it's how we update things. Okay. So before we end, I want to mention this tree diagram. We'll be using it all the time. Okay. We'll use it next class. But let me describe the tree diagram in the last 2 minutes. Okay. So here we do things one by one. So here, this is the first row. Okay. First row here, you can have a first row is black or first row is white. Okay. Once your first row is black, then you only 2 black, 3 white. If you draw is white, then you have 2 white and 3 black. Okay. And suppose you have conditional on you have 1 black, you have 2 whites and 3 black. So which means that if you draw in black, is 2 over 5. If you're white, 3 over 5. Right? That means that if you consider this black 1 and black 2, you just multiply along the way. That is the multiplication rule. The end of the tree will be multiplied along the branch. If you want black 1 and white 2, you just multiply these 2 numbers, give you this one. Similarly, you have done white 1 and black 2, you just multiply along it. Multiply along it, give you the way end answer. Okay? So don't worry about this tree. We'll use it many times to understand the Bayes theorem. Okay? Because in the next class, what we will learn is, okay, suppose something happened, we go back to infer. Okay? So don't worry about that. We will talk about that next class. I see you on Thursday. Have a nice day.